In today's lecture, we will be discussing area between two curves. So let us begin by considering two functions f of x and g of x. And we will consider our function f of x to be greater than our function g of x. Graphically, it would look something like we have a function. Let's say this is f of x. And we will have another function g of x. So clearly, the function g of x is lesser than the function f of x. Our goal will be to determine the area bounded by these two curves on the interval a and b. So this area will be given by integration going from a to b. We'll take the function which is bigger than the other one, that means we have f of x, and from this function f of x we are going to subtract g of x and integrate it with respect to x. So this is going to give us the area of the shaded region. If we want to think about it, what is happening here, when we consider the area under the curve f of x, this is represented by the entire region between a and b and below the curve of fx. And when we consider the area of the curve under the graph of gx, this will be all the shaded region that will be below the curve of g of x. Now what we have done here, we are subtracting the value of or the area under the curve of g of x from the f of x, and that leaves us with only the region between f of x and g of x. So let's begin with our first problem. So here we need to find the area enclosed by the curve given by y equals to x squared and y equals to x. So here we have the x-axis and the y-axis. The graph of y equals to x squared, this will be a parabola, and it is going to be an upward facing parabola with its vertex at the origin. So this will be our graph of y equals to x squared. The other one, y equals to x. So this is a straight line that passes through the origin with an angle of 45 degrees with the x-axis. So this is going to be the graph of y equals to x. Our task will be to determine the area as given by this shaded region. So for this, what we need is our interval. So here we know this is going to be the origin, and we need to figure out this particular coordinate. So this coordinate can be obtained by solving the equation y equals to x squared and y equals to x. So we have y equals to x squared and y equals to x. If we equate the two equations, then we should get x squared equals to x. So we have x squared minus x equals to 0. So x times x minus 1 will be equals to 0. So this gives us two values of x. We have x equals to 0 and 1. So when x equals to 0, we can substitute this value of x in either of the two equations. That is going to give us y equals to 0. So we have one of the coordinates of intersection. So this is 0, 0. And the other one corresponds to. So when x equals to 1, then y will be equals to 1. So the other point of intersection will have a coordinate 1, 1. So we have an interval. So our interval of integration will be from x equals to 0 to x equals to 1. Fine. So let's find out the area of this shaded region. So the area of the shaded region will be given by integration going from 0 to 1. So now we'll have to consider the graph which is above the other graph. So here, if we look at this illustration, we can see that y equals to x, the straight line is above the parabola. So we will consider this particular function. So we have fx. So here this is going to be our f of x, and y equals to x squared. So this is going to be g of x. So we have x minus x squared multiplied to dx. So let's compute this particular integral. So this will be equals to 0 to 1. We have x dx minus 0 to 1 x squared dx, which will be equals to, if we use the power rule, so this will be x raised to the power of 2 divided by 2 minus, we have x squared, so this will be x cubed over 3. Then we have to obtain the value of this particular function at the endpoints 0 and 1, and this is going to give us, we have 1 over 2 minus 1 over 3 minus 0, which is going to give us the value 1 over 6. So 1 over 6 squared units. So this is going to be the area of the shaded region bounded by the curve y equals to x squared and y equals to x. Let us work on another problem. So we have to find the area enclosed by the curves y equals to x squared and x equals to y squared. So we'll begin with y equals to x squared. So this is a upward facing parabola with its vertex at origin. Then we have x equals to y squared. So this is also a parabolic function, which is going to be a right facing parabola with its vertex at the origin. So what we have to do, we have to find out the area enclosed by these two curves. So that means we want to determine the area of this particular shaded region. For this, we need the two coordinates of their intersection. So that means we will have to solve y equals to x squared and x equals to y squared. So this is a very simple equation. So we'll begin with y equals to x squared, and we have x equals to y squared. So we'll substitute y equals to x squared into this equation. So this gives us x equals to x squared whole squared. So this will be x equals to x raised to the power of 4. So if we rewrite this equation, we have x raised to the power of 4 minus x equals to 0. Take x as the common factor. So this will be multiplied to x cubed minus 1. So x cubed minus 1. So this can be extended as x minus 1 times x squared plus x plus 1 equals to 0. Solving, we get x equals to 0 and x equals to 1. This is where we don't have to solve for x squared plus x plus 1, because this is going to give us imaginary roots, which we do not need. Now for x equals to 0, the corresponding y value, which we can obtain by substituting the value of x in any of the two equations, is going to give us 0. And for x equals to 1, we have y equals to 1. So we have our point of intersection. So this is 1 comma 1, and we have 0 comma 0. So we'll integrate the function from x equals to 0 to x equals to 1. So let's perform the integration. So our area, the enclosed area, will be from 0 to 1. Now we have to be a little careful which curve we take first. So we have to consider the curve which is above the other curve. So this is our curve of y equals to, this is y square equals to x. But we want this as y equals to square root of x. We want as a function of, so f of x will be square root of x. And the graph below it, this is the graph of y equals to x squared, which is our g of x. So we want to subtract g of x from f of x. So this will be square root of x minus x squared, and we are going to integrate with respect to dx. So this will be equals to integration of square root of x, which is x raised to the power of half. So this is going to give us 2/3 of x raised to the power of 3 over 2 minus integration of x squared will be x cubed over 3. Then we will use our limiting value 0 to 1, which will be 2/3 minus 1/3. Then this is simply 1/3 square units. So that means the area of the enclosed region will be 1/3 square units. Let's go to the next problem. So here we have to obtain the area enclosed by these two curves, the sine x function and the cosine x function on x greater than or equals to 0. So we'll try to first sketch the graph of y equals to sine x. So our y equals to sine x, the shape of this graph will be sinusoidal in nature. And then we consider the graph of y equals to cosine x, which will start from a value of 1 at the origin. So this will be of this particular shape. So we have to find out the area enclosed by the two curves. Let us consider this particular section. This is the region where we want to find out its area. We can consider other region as well. But for this particular problem, we will only consider this shaded region. So that means we will be needing to obtain the point of intersection. To do that, what we do is we equate the two equations. So we equate sine x with cosine of x. Now, dividing both sides with cosine of x will give us tangent of x is equals to 1. That's because sine x over cosine x, the ratio is tangent of x. The tangent of x equals to 1, so x can take many values. So we will consider our first principal value, which is pi over 4. So that means when x is pi over 4, then y will be equals to 1 over square root of 2, because we can substitute that value either in sin x or cosine x. They should give us 1 over square root of 2. So this is our point, pi over 4, comma 1 over square root of 2. Right. So that means we will begin from our origin x equals to 0 and integrate it up to x equals to pi over 4. So that means the area will be from 0 to pi over 4. Now the question is, which curve do we consider first? The upper curve will be the curve of, this is our cosine function. So let's call it f of x, which is cosine of x. And the curve below it, let's call it g of x. And this is going to be a sine function. So that means f of x minus g of x, that is simply cosine of x minus sine x. And then we integrate it with respect to x. Right. So integration of cosine x, so this gives us the sine function. So we have sine of x minus integration of the sine function gives us negative cosine of x. So this will become positive cosine of x. So we have to obtain its value at the endpoints, pi by 4 and 0. So let's substitute it. So we have sine pi by 4 plus cosine pi over 4 minus the lower limit, which is sine 0 minus cosine 0. We'll continue it here. So the area will be equals to sine pi over 4 is 1 over square root of 2 plus 1 over square root of 2, which is the value of cosine pi over 4 as well. Then we have negative sine 0 is 0 and cosine 0 is 1, which gives us 2 over square root of 2 minus 1, 2 over square root of 2. So that's simply square root of 2 minus 1. And we know the square root of 2, this value is approximately 1.414. So when you subtract 1 from it, this gives us 0.414 square units. So this is going to be the area of this particular shaded region. So let's go to the next problem. Problem number 4, we need to obtain the area enclosed by the graph of y equals to absolute value of x and the straight line 3y equals to x plus 6. So the y equals to absolute value of x. So this is a straight line. So this is the graph of our y. Let's call it f of x equals to absolute value of x. Then we have the equation of a straight line 3y equals to x plus 6. Clearly it has a positive slope. So this is the graph of g of x, which will be equals to 1/3 of x plus 2. Now our task will be to determine the area enclosed by this line and the graph of y equals to absolute value of x. So for this we will be needing the endpoints, which will serve as the limits of integration. Right. So we'll have to find out the points of intersection. To do that, we will solve this two equation. Now let's take two cases. Case number 1, when the value of x is less than 0. In that case, we have y will be equals to negative x and the line remains the same, 3y equals to x plus 6. Right. So we will replace y with negative x. So this will be negative 3x equals to x plus 6, or this is simply negative 4x is equals to 6, x is equals to negative 3 over 2. So when x is equals to negative 3 over 2, then our value of y will be negative of negative 3 over 2. So that's positive 3 over 2. So this point, the coordinate of this point is negative 3 over 2, comma 3 over 2. Now let's talk about this point. For this, we will be considering case number 2, when the value of x is greater than 0. In that case, y will be equals to x and 3y will be equals to x plus 6. So we'll substitute y with x. So that will be 3x will be equals to x plus 6. Solving for x, we have 2x is equals to 6 or x is equals to 3. And when x is equals to 3, then the value of y will be automatically equals to 3 because y is equals to x. So the coordinate of this intersection point is 3, 3. So our limits of integration will be from x equals to negative 3 over 2 to 3. So let's find out the area of the shaded region. So the area will be given by, we have integration going from, we'll break this integration into two parts. So we'll first go from negative 3 over 2, this is your x value, to x equals to 0. Now we'll have to consider gx minus fx at this time because gx is the upper curve and fx is below gx. So in the interval negative 3 over 2 to 0, our gx is x over 3 plus 2 minus the graph of f of x. So f of x here is negative x. So this is dx plus the second integral going from 0 to 3. And in this case, we have gx, which is again x over 3 plus 2 minus fx. Now fx will be simply positive x because we are on the regime x greater than 0. So this is minus x integrated with respect to x. So let's complete this integration. So this will be integration negative 3 over 2 to 0. So we have x over 3 plus x. So this become 4x over 3 plus 2 dx plus 0 to 3. So this will become 2 minus 2x over 3 dx, which will be equals to 4 over 3 times integral x dx plus 2 dx with the limits of integration going from negative 3 over 2 to 0 plus 2 times integration of dx 0 to 3 minus 2 over 3 integration x dx going from 0 to 3, which will be equals to 4 over 3 integration of x dx. So that will be x squared over 2 with the limits going from negative 3 over 2 to 0 plus 2 times integration of dx. So that's simply x values going from negative 3 over 2 to 0 plus 2 times x 0 to 3 minus 2/3 multiplied to x squared over 2 0 to 3. So this gives us our area equals to, we have 2/3, so we are cancelling out 2 from the denominator and 2 from the numerator. So this will be x squared. So we have 0 squared minus negative 3 over 2 squared. So we were using the limits as well. Plus 2 times we have 0 minus of minus 3 over 2 plus 2 times 3 minus 0 minus, so this 2 and this 2 goes away. So we have negative 1/3 x squared. So this will be 3 squared minus 0 squared, which will give us 2/3 multiplied to negative. So 3 squared will be 9 over 4 plus 2 times 3 over 2 plus 2 times 3 is 6 minus 1/3 of 3 squared, which is 9. So this gives us negative 3 over 2 plus 3 plus 6 minus 3. So this 3 and this 3 goes away. So we are left with 6 minus 3 over 2. So this will be 9 over 2 square units. So this is the area, required area, enclosed by the graph of y equals to absolute value of x and 3y equals to x plus 6. Let's move on to the next problem. So we need to obtain the area enclosed by the curves x equals to 4, y equals to 2 and y equals to 1 over x. So let's first sketch the graph of y equals to 1 over x. we will consider x equals to 4 and we have y equals to 2. So let's say this is y equals to 2. So our task will be to determine the area enclosed by the graph of y equals to 1 over x, the line y equals to 2 and x equals to 4. So that means the area of this shaded region. So let's obtain that value. For this, first we will need this intersection point. So the idea will be we will divide this shaded region into two parts so that we have a rectangular region and this particular region whose area we will find. So we will need to obtain this intersection point. So this intersection it is happening between the line y equals to 2 and y equals to 1 over x. So let's solve that. So we have y equals to 1 over x and y equals to 2. Substituting this value, so we have 2 equals to 1 over x. So x will be equals to half. So that means this is the value of this particular intersection point, half comma 2. So this is, so let's perform the integration. So our area will be equals to, for the first region, so we will take the limits from 0 to half. So our upper curve will be y equals to 2. So this is simply 2 minus, there is nothing there. So this is simply x-axis, which is 0. So this will be 2 minus 0 dx. For the next part of the area, we have x running from half to x equals to 4. So we will consider this curve, which is 1 over x minus the x-axis, which is simply 0 dx. So let's integrate this. So this will be 2 times integration of dx going from 0 to half plus integration dx over x half to 4. Integration of dx, so that's simply x going from 0 to half plus integration of dx over x, so that's natural log of x with the limits running from half to 4. So this will be 2 times half minus 0 plus natural log of 4 minus natural log of half, which is equals to 1 plus, so natural log of 4, so this is simply 2 times natural log of 2. We have used the property, so 4 is 2 squared, we have brought the 2 to the front, minus, so we have natural log of half, so this becomes positive natural log of half. So this gives us 1 plus 3 times log of 2. So this is going to be the area of this shaded region. So this is how we can obtain the area under a curve using the formula. Integration going from a to b, f of x minus g of x dx, with the criterion that f of x must be greater than gx. Fine. So let's end the lecture here today. See you in the next class.